5. Okay, so today the objective. What we really want to talk about today is, so it's applications of sine or cosine curves. But specifically on the back side, we want to talk about a damped curve. Okay? So if I look at example 1, 12, 6, 19. If I look at the example 1, this is going to be just a cosine or a sine curve. Because this curve is never going to damp out. Does that make sense? I mean, the amount of sunlight you get varies year to year is not going to change. This, I mean, that would be a weird thing if all of a sudden we got less and less sunlight. Or we could move to the equator and this could change. But if you're one thing, this curve is going to go on and on forever with this shape until the Earth destroys. Obvious, okay? So, before we do anything, let's go back and review. Y equals A trig of B times X minus H plus K. So we did the tide problem, we looked at this formula, right? Where A is the amplitude, B is the frequency, and then H is a phase shift or horizontal shift, and K is your vertical shift. So let's write that down. I know A is the amplitude, and if you can't figure out what the amplitude is, it's the max minus the min divided by 2. B is the frequency, and B is 2 pi divided by the curve width. H is a horizontal shift. But it's the opposite, right? It's the opposite. And then finally, K is a vertical shift. And if you have a hard time figuring out what the vertical shift is, it's always going to be the minimum plus the amplitude. Okay, how am I doing? So far, so good? Well, if I look at this curve, I've got a couple of different choices. Depending on where I want to start. I could start here and call it a sine. I could maybe start here and call it a negative cosine, but I think I'll start here and call it a sine. And again, if you're not sure, I'll put them back up again. You know the sine curves. Sine looks like that, right? Sine starts at 0, right? And a cosine starts up, like if you're going to go to water slides. Water slides would be, you go up the ladder and then you go down, right? That's a cosine. And the sine is if you were to...
You don't go back up.
Huh? No, I agree with that. But where do you start, right? Or think about this, roller coaster. Let's go roller coaster instead, okay? So if you do the roller coaster, you get on the roller coaster here, you go up, then you go down, right? Or the roller coaster starts here at the top and then rolls down. Okay, so it just depends on where it starts, whether it's sine or cosine. So I actually want to start on this one. Let's call it a sine. And the reason I want to call it a sine, it'll make sense to you, is because this value is not really the minimum. It's December 21st. Isn't it? Isn't the minimum December 21st? Right? So January 1st is not the minimum. We know that. The winter solstice is December 21st, which would be back here, okay? So we do know that's the spring solstice, so that's a for real midpoint. Okay, everybody good on that? So let's start off with this. Let's start off with y equals a sine. Okay, let's just start off. Y equals sine. We're going to call it a sine curve. Now the amplitude, well, it sure looks like it's 3, doesn't it? You guys see the 3? If you're not sure how to get the amplitude, we can get the amplitude from the max, which is 15, minus the min, which is 9. 15 minus 9. So if I go 15 minus 9 divided by 2, 6 over 2, which is 3, right? But you can see that. Can't you see that? Up 3, down 3. Got the amplitude is 3. Now, B. B is a frequency. So to get B, we're going to take 2 pi and divide it by the curve width. Now, don't let the curve width fool you. It's super easy. How wide is this curve? It's super easy.
Oh, 9 months. Nope.
March, April, May, June.
Super easy. It's so obvious.
1 year.
1 year.
Oh,
Isn't it 1 year?
no.
From, so 1 year. So if you go 1 year from like winter solstice to back to winter solstice, it's 1 year, right? It's 365 days.
Were we starting at winter solstice?
February to
Wherever
December.
you start, a full curve would be end in the same spot, right? So wherever you start, so let's say you start the curve here, you'd end in the same spot. So if you start at the spring solstice, you'd have to go and end in the spring solstice. How many days is that? 365. Okay. So it is 2 pi divided by 365. So my curve is going to be 3 sine, and we'll get a 2 pi over 365, parentheses, x, right? Or t. I like t better than x. How about t for time, right? And t. Now, what's the shift? Well, it's March 21st, right? How many days? Or how many days is it from 0, which is January 1, to March 31st? Well, let's do the math. Let's do the math. Okay, so we can do this. We can do this. So January's got how many days does January have in it?
31.
Plus, how many days does February have on it? And normally 28. And then we're going to go to March 21st, right?
It's 80.
So add 21, and what'd you get, 80? So that means this number right here is the 80th day, okay? So this number here is the 80th day of the year. You with me? So my shift is t minus 80, okay? Plus k. Now hopefully you can see the midline. You guys see the midline? What is the midline? 12. And if you're not sure how to get the 12, again, it's the minimum, which is 9, plus the amplitude, which is 3, which gives you 12. Okay, so here's my equation, right? Here's my equation. Good. All right. Let's see what we can do with that equation. So first of all, question A. Does the daylight change more rapidly? Now, this is really a kind of a calculus question, but it's easy. Does the daylight change more rapidly in July or in September? Does the temperature change, or the daylight change, does daylight change more rapidly in July or September? So July is right about here, and September is right about there. Yes, how do you know that?
It goes down.
It's the middle of it.
Goes down how?
Faster.
Yes, faster. It's a rate, so it's a slope. So think about slopes. Now, this is a real calculus thing you're going to learn. The slope up here, what's the slope way up here? What's the slope right there? About 0, right? The slope here, barely any slope, barely slope. So the slope is a rate. It is a rate. And when I get to September, the slope is greater, which means we lose more daylight per day, right? Does that make sense? And sure enough, when you get to in here in September, we start to lose the days. Every day we lose about 3 or 4 minutes per day, right? Here's where we're at right now. It kind of sucks. Do you see what I'm saying? It kind of sucks. But you love it. If you're a summer person, of course, this is good. This is good. These are your dog days of summer. They seem to last forever, don't they?
No.
Because the sunshine sticks around and slowly disappears. This is where we're at right now. The sun's coming back on December 21st. It's slowly going to come back. Does that make sense? You see the slope? Remember the slope of the curve?
Wait a minute. It's going to come back pretty fast.
No, it goes very slowly. In fact, we can look it up on our phone later. I can show you this little app. So not until you get to the spring solstice does the sun start coming back pretty rapidly, okay? In fact, we'll look it up when I'm done recording, okay? So it's going to be more rapidly in September, okay? What's the period and amplitude of this? Well, the period's what? 365 days, yes. My amplitude is what? 3. So it means 3 hours of sunlight we gain from the equinox to the solstice, and 3 hours of daylight we lose from fall equinox to the winter solstice. Okay? Good. Now, find a sinusoidal. Ooh, that's a weird name, but that's what we just did. It is, our sinusoidal equation is y equals r3 sine of 2 pi over 365 t minus 80 plus 12. How am I doing? Let me put that in a darker pen so you can see that better, okay? Y equals 3 sine 2 pi divided by 365 t minus 80 plus 12. Okay, everybody good on that? Now, what's the amount of daylight on January 1st? Okay, so January 1st would be what day?
0.
Day 0. So, what I want to do is plug in t equals 0. Okay, so I'm going to plug that in my calculator, right? Before I do anything, let's change our mode. What am I going to change my mode into? Let's change our mode
Radians.
into radians. It's got to be radians because we're working with 2 pi. Agree? Radians. And what I'm going to do is go y equals 3 sine of 2 pi over 365 times the 0 minus 80 plus 12. Okay, and I'm going to put that in my calculator. I really will. Okay, so on. Okay, in fact, what's really easy is I'm going to actually graph it. If I graph this, it's going to make it even easier for me. So I'm going to go to y equals mode, first mode, radian. Can you guys see this? Yep, rad mode. I'm going to graph it. I'm going to go y equals, I'm going to go 3 sine parentheses. I'm going to go another parentheses. Trust me, I'm going to go 2 pi divided by 365 parentheses x minus 80 parentheses. Do I need one more parentheses? I think so. Plus 12, okay? Now, window. What's my window going to be? What's my window going to be?
365.
0 to 365. And this is going to probably go from maybe I got to go from a 9. So let me go 6 to probably, let's make it 18 so we can see the whole thing. So let's graph it. There it is, right? That's exactly what I had. Now, how's this going to help me? Well, if I want to answer day 1, or day 0, really, day 0, I can just go to trace 0. Okay, how much daylight do we have? About 9.07 hours on that day. No, it's not. It's worse for us because we're higher up than Denver, Colorado.
Wait, we're higher than.
We're not higher than
No,
Denver.
we're not. They're a mile high, right?
They're way higher than us.
I'm sorry,
We're
longitude. More north.
Okay,
Longitude.
yeah.
I was like,
Longitude.
We're like 1,300 feet. They're
no,
like,
we're like 1,200.
No, I said wrong. Latitude.
Yeah.
That'd be wrong.
Latitude,
More
right?
northern.
Yeah, we're more northern, so we get less sunlight, unless it's summertime, and then we get more daylight. Okay, so about 9. So Denver, Colorado is going to get about 9 hours of sunlight January 1st. Now, how about July 4th? How about July 4th? What am I going to find for July 4th? July 4th, let's figure it out. July 4th, okay? How many days?
185.
How did you get 185 so fast?
I did it before you.
You did January plus
No.
February plus March.
No, you just took
You're way too smart. Let me do this. January, February, March, April, May, plus 4, right? Okay, what'd you get, 180?
185. Wait, did you forget June? You forgot
January, February, March, April, May, June. Thanks, Makaiwa. Okay, so let's figure out what 185 is. Okay, so trace 185, about a 14.9 hours. Now, another way to do this is you just could have plugged in instead of graphing. I like the graph. It's easier. I think it's easier because you can use trace button. The other way is you could have plugged in 0 for t and just use your calculator. Or you could plug in 185.
I plugged in 185, and was I supposed to be in radians or degrees? 'Cause
Radians.
I put it in as radians, and I got 17.42 hours.
Can't be. So there's something wrong with the way you put it in. Can't be because, you know what it can't be? The highest ever going to get is 15.
Yep.
So Makai would check your formula. Now, one way to make it easier to plug your Makai, are you ready? One way to make it easier to put in your calculator is figure out what this is as a decimal, and just
It's
get that to the nearest
point,
thou-
0.0172.
0.0. Say it again.
172.
Try that, Makaiwa, and see if that helps.
Oh, I'm not really that worried about it.
Okay, thank you. Thank you. Okay, now, not bad. Not bad. Okay, you ready to turn the page?
No. Could
Okay.
you get it down a little bit?
Yeah, there you go. Okay.
Okay.
Okay, 14, so.
Okay.
So that's a continuous curve. I mean, this is never going to change until the Earth blows up, right? We're going to have seasons, we're going to have our summers and our winters year after year, till we're, even after we're dead and gone, right?
What's with you and the little planet?
What?
Do you have a plan to?
No, it
Blow
will
down
blow
the
up.
babies?
It will blow up someday. It will.
The sun only has like 4.5 billion years.
Yes, so 4.5 billion years it's going to be
Give or
like
take a few billion.
Yeah,
the
give or
sun.
take
And
some.
you guys know if you've taken plants, the sun's going to go like this. It's going to expand, right? When it finally becomes unstable, when
sun's
all
gonna
of the hydrogen's burned up and it starts to burn its helium, the sun's going to go like this.
Why is the flag moving?
Those heat. Okay, turn the page. Ready? So let's take a look at the back side. So on the back side, we need to write this formula down. Y is equal to A,
Can you move it down?
yep, Y is equal to A E to the CT sine of BT. This should be a negative though. Or y is equal to a e to the negative ct cosine of bt. All right, write those two formulas down, please. Okay. Sure, I know exactly. I'll check on my formula while you guys are writing that down. Yep, I'm right. Okay, now. How do we know if it's going to be a sine or a cosine? It just depends on where it starts, right? Here, though, it's different. Okay, here it's different. Okay, I'll just write a picture. Okay.
Do you need new markers?
Ah, yeah, you got some of that. So you ready? Watch. We watching? Take a spring. You watching? This is my favorite part. Love this. This is fun. This is where I get to do something. Okay, ready? Watch. Stretch my spring. Let go. It goes boing, 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 boing. Right? You hear that? That's a damp curve. And when we get the E to the negative CT, that makes it go, right? Got it? Now, the stiffer the spring, the faster it's going to go, right? The looser the spring is going to go, got it, right? So you get this constant C, which gives you, in a sense, the stiffness of the spring, okay? So let's take a look at number one, okay? So, you have a spring is stretched to a length of 10 centimeters, so it's brought up to 10. So let's just go straight to our graph right at the bat. Let's go Well, let's go 2, 4, 6. I need to make it all the way to 10. So let's go 2, 4, 6, 8, 10. Negative 2, negative 4, negative 6, negative 8, negative 10. Okay? So I stretch my string. My spring is all the way up here at 10. Okay? I pull it up, right? And when it is released, it's going to go. Does that make sense? Does that make sense when I release it? So, my amplitude has got to be 10, right? It's going to start up here. And it's going to go like this. It's going to go, and it's going to curve down, something like that. You guys agree? So this one's going to be a cosine. Can you see it? It's going to be a cosine. So let's go back up and make a formula. So I'm going to go to y equals 10 cosine. Oh, I'm sorry. Y equals 10e to the negative ct cosine of bt. Okay, so far so good. Now C has to do with a dampening constant. So we're given dampening constant 0.2. Okay, that's the stiffness spring. So we're going to point 2 there. Okay. So I'm going to go. Okay, I'm going to get a y equals a 10 e to a negative 0.2 t cosine. Now B is always the same thing. B is always 2 pi by the curve width. So it goes back to its original position in half a second. So the curve is a time, but it's half a second. So the curve width is going to do this in half a second. So the curve width is half a second. To find B, we'll just take 2 pi divided by 1/2. Okay? So 2 pi divided by 1/2, and if I simplify that, then B is 4 pi. Now, to do the rest of this, we can plug in 3 in for t, right? So B, what is the height of the spring after 3 seconds? Well, let's go y equals 10 e to the negative 0.2 times 3 cosine 4 pi times 3. Okay, and I'm just going to use my calculator, radian mode, right? Got to have radian mode. Let's just see what I get on my calculator. So clear, quit. So I'm going to go 10, and I'm going to go, my E button is down by the natural log, right? E to the negative 0.2 times 3 cosine of 4 pi times 3. Okay. I get an answer of 5.5. That's the height of the spring. So it's a loose spring. It's got to be a really loose spring because
Do you have any?
I don't. Mr. Massey does. Okay. So at 3 seconds, our spring is at 5.48 centimeters. Okay. Now, if we have to graph this, it's a real pain to graph by hand, but if you put it on your calculator, it's not too bad. So how do you put it in your calculator? So I'm going to take my equation right here, and I'm going to put it in my calculator because it makes it a lot easier. So I'm going to go to my y equals, clear that old thing, 10 e to the negative 0.2 x. It's got to be x because there's no t. Cosine of 4 pi x, right? Now let's adjust the window. So the window I'm looking at has got to be different from my last window, right? So my window is going to be from negative 10 to 10, but I'll go a little higher than 10 so I can see it. How about if I go negative 12 to 12? Scales by, let's make scales by, I'm going to go scales by 1/8 of a second. 1/8 of a second. My y min 0 to, let's go 4 seconds, okay? Let's go 4 seconds, all right? Graph. Oh, and something's terribly wrong. Something's terribly wrong, but I'll fix it in a second.
Oh my good night.
What?
Why did that
What?
Sign, we're gonna design.
Something's terribly wrong. So so the first thing I'm gonna check is my mode, right?
Something is terribly wrong.
What?
Let's check my mode first. I'm in radio mode. Let's check my window.
Maybe this is the answer.
Negative 12 to 12. Oh, negative 4 no, 0.
Leave it alone.
No. 0 to 4. And negative 12 to 12. That was what, there we go. There's my spring. Does that look better? There we go.
Oh, look, it's getting short.
Oh, yeah.
There's my spring. Right? So let me go and do half a second, 1 second, 1.5, 2, 2.5, and 3. I already know the answer to 3. I do. The answer to 3 is a 5.5. Okay, I already know the answer to that one. I got that from above, right? And now what I want to do is put this picture, I want to put this picture on my graph. So let's use the trace button, okay? So if I go and use my trace button, right? And I don't have to have all of it, but if I get a general picture of what it looks like, that's about 0.25 is about a negative 9. 0.25, which is about 1/4. Okay, 0.25 is about a negative 9. It's about there. 2, 4, 6, 8. Okay. Trace. At about 0.5, we're at about 8. So it's starting to look like this. Keep tracing. At about 0.75, negative 8, 0.75, negative 8, it's about there. Okay. At 1, we're about 7.8, maybe about there. Oops, 7.8, oh, no wonder. And then at about 1.25, I'm negative 7. 2, 4, 6, 7. Right? Trace. About 1.5, I'm about 7. 2, 4, 6, 7. Okay. Trace. At about 1.7, about negative 7. 2, 4, 6, 7, right? About 2 and about 6. 2, 4, 6.7, maybe there. And it's slowly dissipating. Okay, and it's just going to keep going. Smaller and smaller and smaller and smaller. So it looks something like that. What do you think? It's getting hard.